Cohort study. And for those of you who are already practicing occupational epidemiologists, this will be a very basic presentation. So my aim was to try to bring the group to at least an initial understanding about the common methods that are used in occupational studies. So with that, I have basically 4 learning objectives for you. The first is for you to recognize the importance of occupational cohort studies. Second, to refresh your understanding of rates and ratios, because these are very important. They're basically the currency of occupational cohort studies. Third objective is to help you learn about occupational cohort design and some analysis methods. And then lastly, to explore how occupational cohort studies may be used in risk assessment to set occupational exposure limits. And here I'll use an example from my own research related to beryllium work and cancer. So let's see if I can advance my slides. The first part, just about highlighting some of the important aspects of occupational cohort studies. Why would we want to study occupational disease? I hope you're all convinced that it's important. From my perspective, it affects all of us because almost everyone is in the workforce, at least at some point in their lives. And among workers, the burden of attributable disease can be very large. I won't have time to really go into attributable risk calculations, but I've provided in the slides that you'll have copies of some examples in my extra material. We also know that exposure in occupations can be reduced through a variety of proven interventions. And then lastly, I would contend that the occupational cohort study has been the single most important study design in helping to identify carcinogens. So just to illustrate that point, studies of workers have had a major role in identifying human carcinogens. Of the 121 agents that are classified by my organization, IARC, in Group 1, which you'll hear much more about in about an hour or so, 59, or just about half, have been classified on the basis of occupational studies as having sufficient evidence of cancer in humans. So these 59 agents include a series of occupational exposures, but also occupations and industries that are considered to cause cancer without identifying the specific agent. For example, exposure as a painter. So to look more closely at this, at the time of a very nice paper that was written by my former colleagues in this program, Dana Loomis et al., they analyzed the then 120 Group 1 agents and found that 70 of these had occupational exposure associated with them. And most of them, 63, had found sufficient evidence in humans. And of these, nearly all, 59, had some occupational exposure data, occupational epidemiology data, usually from cohort studies. So just to show you some of these here, the ones that are highlighted in yellow have cohort studies associated with them and probably leading to the greatest source of evidence. One commonality is that cancer sites that have sufficient evidence for the physical agents, the dust, fibers, and the metals group typically have this evidence in the respiratory tract. Looking at a similar example of the chemicals groups, most of the common cancer sites with sufficient evidence are in the lung, liver, bladder, skin, and the lymphatic and hematopoietic system. So often the sites of first contact or a metabolic pathway that leads to that exposure. And once again, you'll see that the vast majority of these agents had cohort studies forming the large basis of sufficient evidence. And then just to drive the point home even further, when I was fortunate enough to work at NIOSH in the US, we had established a number of very important cohorts from the 1980s through the 2000s. And I was lucky enough to work on many of these, which were studies of workers in cohorts, defined cohorts of workers, and many of them led to Group 1 evaluations. So then moving on to some of the challenges of cohort studies and occupational epidemiology in general, well, it's certainly true that they may be controversial. The study findings, as you can see, have the potential to influence policy because they're so convincing. And then they have economic and social consequences. As a result of this, diverse actors can have an interest in research findings, and the methods are often subject to scrutiny and criticism. Results may be challenged, reinterpreted, and reanalyzed, which can be great when you have a diversity of viewpoints looking at the same data sets. However, it can also lead to delays in getting out really critical studies. As one example, a major US study of diesel fumes and lung cancer, which was conducted in the setting of an occupational cohort study, took 20 years to complete. It was finally finished in 2012. And it was estimated that about half of that time was spent battling industry obstruction to the study even being conducted and released. So it's I would say, a field not for the faint of heart. Another issue is that access to workplaces is often difficult. And one reason places like NIOSH are so successful is that they have a statutory right to access workplaces for these types of studies. In addition, the pace of change economically and socially is also very challenging. There are over 50,000 chemicals currently in use in industry, with about 500 new chemicals being introduced each year. However, health effects have been studied for only a small proportion of this number. As one example, in the US, the Occupational Safety and Health Administration regulates occupational exposure to only about 400 substances. So there's clearly a lot of uncertainty out there about health effects of these many different chemicals. And in addition, there are other exposures of concern or interest besides just chemicals. In the second part of this particular lecture, I'm going to give you a bit of a refresher on rates and ratios. And I understand that you've all had an introductory epidemiology course at least, so this will be truly a refresher for you. So a true rate can be distinguished from a ratio in the sense that it's a dynamic quality. It's an instantaneous change in one quantity per unit of change in another quantity. And that quantity for epidemiologists is usually time. The rate has no finite upper boundary, unlike a ratio, and it does have a dimension, units. An incidence rate, therefore, is an instantaneous potential for change in the disease state. It's the occurrence of new cases per unit of time, t, relative to the size of the disease-free population at that time. This is sometimes called hazard, and it's expressed in units of inverse of time. And if this is not sounding very familiar to you, then I have some auxiliary slides that you can access with the rest of my slides that will show you this in some illustrations. The most common measures of disease incidence that are used in cohort studies are measures of risks and measures of rates. So one common measure is the cumulative incidence, which is the number of new cases divided by the total number at risk. Now, this can be calculated in a number of different ways, and one of these is called the actuarial method, which takes into account the fact that not everyone is being followed for the same amount of time. So this method allows you to calculate as your denominator the effective number who are at risk at the given time interval. So it's an adjusted method. A separate calculation, which is commonly used in cohort studies, is called incidence density. And this is a concentration of new cases per unit of accumulated population time. So its dimensions it's certainly not limited to 0 and 1 like a cumulative incidence would be, but it's the range may be 0 to infinity, depending on the units of person time that you're using in the time dimension. It better represents the force of morbidity on the population than does the cumulative incidence. However, it has not such great interpretation on any individual person's level. So to illustrate what we mean by incidence density, take this very simple graph showing population size on the y-axis and time on the x-axis. At any time, as time moves along, you have this cohort that's depicted by this curvy line. That's the population size at a given time point. And throughout this, you're going to have cases occurring. And this hatched area illustrates the follow-up time for the study that you're undertaking. Well, incidence density would be the number of new cases occurring during this hatched time divided by the area of the polygon in the hatched area. So this would be 5 per person time unit. So just to recap, how would we measure incidence? Cumulative incidence Simple cumulative incidence is just the number of new cases times TI divided by the number alive at the initiation. This is used when no loss to follow-up occurs, and you will have all experienced simple calculations of data with this sort of measure. The actuarial method is a bit more elegant than this, and it was used before the introduction of very powerful computing methods a couple decades ago. You can also use the Kaplan-Meier method, which calculates cumulative survival functions, with S being 1 minus the cumulative incidence. All of these are expressed as proportion, whereas incidence density is expressed as number of events per person time unit. So this has some related topics then relating risks to rates. Risk is a conditional probability. Its range is 0 to 1, and it's dimensionless, although it does require a period referent. An example of this is the cumulative incidence. Whereas a rate represents the instantaneous potential for change. Its range is 0 to infinity, and its units are the inverse of time. It doesn't require a period referent, and some examples are the hazard rate or incidence density. I won't go into detail, but there is a way that you can relate the incidence density to cumulative incidence, but it does require that this incidence rate be constant over an interval of time. So when would we use risk versus rate? Risk is used to predict individual probability of disease occurrence. It's used a lot in clinical settings to assess patient prognosis or selecting appropriate treatment strategy. Whereas rates are used when person time data are available and is used to test hypotheses about etiology. However, when the disease is rare, you can compute risk in addition to rate using incidence density. So thinking about all these things, I hope I've convinced you now that occupational cohort studies are, generally speaking, much more interested in phenomena related to rate than to risk. And now we'll discuss how this happens in occupational cohort design and recapping some common analysis methods. So the principal measures that are used in these cohort studies, well, basically all occupational study designs combined, are measures of frequency or occurrence. Incidence is measured in cohort studies, whereas prevalence could be measured in cohort or cross-sectional studies. Measures of association can be measured in different types of studies. A relative risk would be measured in a cohort study. A rate or hazard ratio can be measured in a cohort or nested case control study. An odds ratio can be calculated in a cross-sectional, cohort, or case control study. Measures of potential impact, including the attributable risk, or AR percent, and the population attributable risk, and PAR percent, are measured in cohort studies. And I've given some examples in my extra slides because I won't have time to go through that today. But this slide illustrates that cohorts really are built to carry out virtually all the types of analyses that would be useful in a population. There are different types of different perspectives on study designs depending on where the study data are in relation to the person conducting the study. In a prospective cohort study and in a randomized trial, sitting from the viewpoint of the present, the cohort is defined in the present, and then disease experience is recorded going into the future. In a historical or retrospective cohort study, the cohort is defined at some time in the past, and then disease experience is recorded up until the present. And it can be carried out even into the future, but the time point of constructing the cohort is in the past. In a case control study, cases and controls are ascertained from some source population in the present time, and then the exposure history is recalled. You may be familiar with a graphic like this that compares different study design attributes across different study designs. So cohort studies, whether prospective or historical, really do meet many of the objectives of an ideal study. They permit individual exposure and disease outcome to be measured. They allow the establishment of temporality. They have minimal potential for recall bias because generally exposure data is collected before disease is observed. They have minimal ethical concerns, at least compared to a randomized trial. And at least one of them can be conducted fairly quickly. That is the historical cohort study. And by fairly quickly, I mean on an order of a couple to 5 years, as opposed to decades for an outcome like cancer. They're optimal for rare exposures, and that's often why we want to conduct studies in occupational settings. However, they're not optimal for rare diseases, and this can be an issue, low power, when you've identified the perfect cohort. If you don't have enough outcomes because the study population isn't large, then that can present a concern. It also has potential to present confounding, which we'll talk about briefly in a minute. So the basic approach to a cohort study that you all learned in Epi 101 is that a cohort allows you to identify groups of people, cohorts, who are potentially exposed at different levels, ideally, to the agent of interest. Exposures are assessed for each cohort member, and they're grouped by exposure level. They're followed up for a period of time, and disease rates are compared between the cohort exposure groups using some of the rate methodology that I described earlier. They could be done prospectively or retrospectively, and really the analysis is identical for either viewpoint. And very powerfully, we can evaluate multiple diseases for each exposure of interest. Some of the limitations of cohort study designs include the potential for bias. So selection bias, which means inclusion into the study, is related to both exposure and outcome. This is fairly atypical in most records-based cohort studies because you usually know what the sampling frame is for your study base. However, for questionnaire-based cohort studies, selection bias can occur if agreeing to be in the study or even being alive to agree to be in the study is dependent on disease status, which it often may be. Another common source of bias in cohort studies is information bias, in which exposure or outcome misclassification depends on outcome or exposure. Cohort studies, like all epidemiology observational studies, are also subject to potential confounding. And a confounder is a factor that's related or tangled with both disease risk and the main exposure of interest. Examples could be that workers who have higher exposures to the agent of interest may also have co-exposures to other risk factors for the same disease. One often hears smoking brought up as a confounder of concern. However, research has shown that this is less frequently a concern or a major source of bias when comparisons are made within cohort among groups of workers with different exposure levels to the agent of interest. Now moving on to some of the cohort types. In a static or fixed cohort, everyone enters and leaves at the same time, except cases. This simplifies calculations, but of course this is very, very uncommon and almost unheard of. Instead, virtually all cohorts are dynamic or variable. New cohort entries occur across time, and also departures or loss to follow-up occur over time. This is very common in industrial and military cohorts. Employees enter when they're hired, and this makes the analyses more complicated because that process can lead to bias if not adjusted for properly. But both of these types, static or dynamic, can apply to either prospective or historical cohorts. So we've seen this simplistic approach to evaluating the rate ratio between exposure groups in a study, and that emphasizes the fact of failure, failure being the way that we describe case occurrence, that is the development of a disease. However, this is problematic for several reasons. One of them is that the disease may be common and therefore failure may eventually happen to everyone. For example, if you were conducting a cohort study of people's exposure to, I don't know, any common occupational exposure, and your outcome is death, well, everyone will eventually die. So fact of occurrence is just not that useful here. Another problem is that risks of of disease following exposure may be different across different periods of time after exposure. And the simplistic calculations don't allow you to capture that temporal pattern. In addition, simplistic methods of handling withdrawals will either overestimate or underestimate risk. And what are these reasons? Well, why do people withdraw from cohorts? It could be death from a cause not of interest. It could be loss to follow-up because follow-up mechanisms are seldom 100% accurate. Or it could be removal from the at-risk group. A typical example is in a study of uterine cancer, it should only include women with intact uterus. Those with hysterectomy would not therefore be at risk of uterine cancer, and they should be censored or removed from the study group when that event occurs. Okay, so what are some of the alternatives to a simplistic cohort for risk analysis? How about handling of withdrawals? Simplistic method number one would be to ignore the person time contributed by those who withdraw from the study, that is to delete them. This would be seldom done in practice, and it would tend to overestimate risk. Another approach is to assume that the withdrawn person survives event-free to the end of the study. This is commonly done in practice, and it would tend to underestimate the risk in that cohort. You could use the actuarial method for cumulative incidence calculation. This is cumbersome, and as I mentioned, it's sort of an antiquated form of control. It doesn't allow for easy ways to adjust for confounders. More typically, and this was a development that started in maybe the 1970s, using person years analysis. This accounts for person time contributed to the cohort, and it's similar conceptually to the incidence density method. You can adjust for some confounders easily by standardization, and there is customized software available. So in my background at NIOSH, we spent a lot of time working on this computer program called the NIOSH Life Table Analysis System, which is a person years analysis program. And although it's not sophisticated computationally, it's very, very useful, especially if you're comparing cohorts to the general population. More recently, and this is a development of still decades ago, survival analysis, measuring time to failure as the event of interest. Withdrawals are considered censored no matter why they happen. And these approaches are readily implemented in a variety of different computer programs. It allows easy adjustment for confounding via multivariable adjustment, and even effect modification can be fairly easily evaluated. So now I'm going to go into some of the conceptual ways that we think about cohort construction. And to do this, I'm going to tie together this discussion we've been having about different measures of cohort incidence. You'll be seeing this picture a lot. This is a very, very simple cohort of 12 people, and you should be able to see quite easily that this is a dynamic cohort because people are entering and leaving at different times. An X represents the occurrence of an event of interest, and a O represents a withdrawal for some other event, or no event, but just loss to follow-up potentially. So we could ask, between 1998, the start of the study, and the end of the study, 2005, what is the incidence of first occurrence of disease? So you could calculate a simple cumulative incidence of, let's see, 1, 2, 3, divided by 12, which gives us 0.25, right? But that doesn't account for all of this, the fact that people were not under observation the entire time during the study. You could use the actuarial cumulative incidence calculation, and here we would calculate 0.46 over this 7-year period. So again, I didn't show you how to do that, but it's available in different textbooks if you'd like to see. But this gives you a sense of how important the dynamic cohort is to getting a true picture of what the incidence is. So we have a near doubling of cumulative incidence when we take into account the fact that people weren't followed for the same length of time in this cohort. The third measure is incidence density, as I mentioned. So how do we calculate incidence density from this example? Well, we know the numerator, it's 3 observed cases, and we have to count the number of person years. So literally we can sit here, and I would invite you to count them. This person contributes 3.5 because they had the event at 3.5 years in. They stayed on study, but this is not relevant exposure or relevant time on follow-up after the first event occurred. But you can see that people contribute different amounts of person time to this example. And I invite you to calculate it. Hopefully it adds up to 40 person years, and the incidence density would be 3 per 40 person years, or 7.5 per 100 person years, or 75 per 1,000 person years, et cetera. So why am I going through this belabored example? Well, it's because of the concept of incidence density sampling and setting up of incidence density risk sets. And these have really been very successfully employed in occupational cohort studies, and I think is one of the nicest advances to thinking about cohorts. So we're trying to think about analyzing this cohort just as if we were using the incidence density, which, as I mentioned, is a better way of estimating rates. How do we do that? Well, what we do is we enumerate risk sets. So for each case, we identify who is in the risk set, what other cohort members are in the risk set. So for the person number 8, who is a case here, the people in the risk set are the people whose person time at risk intersects with that of the case. So person number 1, not in the risk set because they already had the event at an earlier time point. Person 2 withdrew before the event occurred, so they're not in the risk set. Person 3, person 4, they are in the risk set, and et cetera. You can see exactly who is in and who's not in the risk set. So there are really 4 people in the risk set for person number 8. For person number 11, there are also 4 people, but they're different from the 4 that we saw before. And then for person number 1, we have 6 people in the risk set. So conceptually, this is how risk sets are enumerated. And then you can take it a step further by sampling from the risk set. And so for this case number 1, we might decide that we will be sampling 3-to-1 case control rate ratio. So this is, in fact, the basis of the nested case control design. And you would use this design when it's more efficient to estimate exposure or confounders for people who are for the people who are in your study. So this is a basis of having a very efficient and asymptotically identical result to a full cohort analysis, but using a selection of the risk set as controls. So what you should then, well, to continue this thought, how do we ensure that we have an unbiased estimate of the exposure for these risk set members? The simple solution is you ignore any exposure that occurred after the time point when the case became a case. So in these examples for person number 3, who was selected, you would only measure exposure up until halfway through 2001, because that's when the case that they're matched to failed. So that is how you kind of recreate an unbiased estimator of the exposure-related risk. This is an unlagged exposure example. We could also look at a 2-year lagged exposure in which we're discounting or not counting the exposure that occurred within 2 years of the case failure. So here we see that we would only count exposure for the risk set up until midway through 1999 for this particular risk set. Hopefully that's clear for everyone. And there are actually computer programs that will calculate this stuff for you. These are risk set based cohort studies, and a nested case control study is just a very special example of this. Now, I showed you calendar time as the time scale. However, the choice is up to the investigator. It's flexible. And we say that the best choice is usually the most important confounder, the thing that you'd usually have to control for very tightly anyway, because this is considered an exact form of matching. So age is often used, attained age, as the time scale. And in a study that I'll show you shortly related to Beryllium, that's in fact what we did. But you could use follow-up time if that's an important factor. You could use age at risk, or you could use calendar year. So case and control exposure, or case and risk set exposure occurring after the case failure time, whatever that scale is ignored in order to carry out unbiased analyses. The analysis is done by conditional logistic regression. This is asymptotically equivalent to the Cox proportional hazards model. And the odds ratio is interpretable as a hazard ratio or a rate ratio. No rare disease justification is needed. So It's a very, very special and powerful design that's become quite useful in occupational epidemiology. However, you should be cautious about further time factor adjustments because you want to avoid multicollinearity. This is because calendar year minus attained age is equal to year of birth, and age at first exposure plus follow-up time is equal to attained age at risk. So that does require some caution. All right, well, this is an approach to design and analysis of a cohort study that takes into account this concept of incidence density as the basic currency of occupational cohorts. How do we control for confounding? There are many different ways to do it. You could control during the design phase, as you could for any type of study. In restriction, we study only certain subgroups. For example, just men or just women. You could exclude certain race or ethnicity groups. You could restrict your study to only non-smokers to tightly control for smoking. You could also identify persons who are not exposed to other potential confounders, that is, other risk factors for the outcome of interest. And in these instances, internal validity is improved at the expense of generalizability. And I think with greater attention paid now to issues of social justice in studies, it's getting harder to justify using restriction by sex, race, ethnicity, et cetera, in the design phase. You could also match on confounders, although this is not often used in cohort studies. But I showed you an example of using incidence density sampling to exactly match on age. And age is one of the most important confounders in just about every outcome that you could conceive of. When you're restricting, you cannot evaluate interactions of the exposure and the confounder. However, you can when you're matching under some circumstances. You could also control during the analysis, which is much more common these days. Standardization, as I mentioned, is commonly used for external comparisons, and we often standardize on things like age, sex, race, ethnicity, calendar year, things that are variables that are available not only at your cohort level, but at the external comparison population level as well. You can use the Mantel-Hansel approach for matched cohort data, but as I said, that's not very commonly used, matched cohort studies. You can use Cox proportional hazards model for unmatched cohort data by employing risk sets, setting up risk sets, as I showed you in the previous slide. And very commonly, you can use Poisson regression for grouped data. However, that does require stratification of most approaches require stratification on whatever your confounders and exposure variables of interest are. So you do lose a bit of perhaps statistical power when that's done. All right, now turning to the more mundane, what are some data sources for occupational cohort studies? For both roster and exposure data, we may often rely on existing records. These could include industry work history records. Here, there's a need to ensure consistency and accuracy, completeness of these records. Quality control measures must be employed for abstracting and coding the information. And in the example that I'll show for Beryllium, this was a huge issue because we had to go out to the factory and literally go into records and collect and abstract them. And you're often faced with difficult decisions about missing data and how to deal with it. You also need to consider whether to carry out an incident cohort or a prevalent cohort. And what do I mean by that? Well, in an incident cohort, you include everyone who was involved at the facility from the time that it began or the time that exposure began. This is really preferred because it helps avoid healthy worker survivor bias, which may affect your cohort study. But sometimes it's unavoidable that you have to use what's called a prevalent cohort, which is where you start with people who were already employed at some point in the cohort establishment. Another source of data for rostering and exposure is questionnaires and interviews. These require standardization. Many instruments, particularly for outcome evaluation, have been standardized and they're available online. However, even if you do obtain them online, they must be pilot tested to evaluate the suitability for the population of interest. Mailed questionnaires can be especially prone to bias. Interviews are generally thought to be higher quality, but questionnaire studies are often subject to selection bias, as I mentioned earlier, because not everyone will respond, and response can be related to disease status. You could also measure current external exposure or biomarkers to assess exposure. Or you could rely on historical exposure monitoring data. And I'm sure you're going to have some presentations by other speakers about the development of modeling to classify the cohort by exposure groups. You can use job exposure matrices to do such things. It is important to note that often in cohorts, a typical pattern is that earlier data will be less reliably measured, less reliably available, and subject to greater measurement error. And they're also tend to be higher because a common pattern is that exposure tends to decrease over time in occupational cohorts. Outcome data can be also obtained by questionnaires, interviews, and these are susceptible to selection bias if the response rate is affected by disease status, as I mentioned. Proxies can be used to help avoid this. However, the proxies may themselves not be suitable. They may not remember exposure very well, and this can lead to further bias in exposure estimation. Record linkage is often used with death registries or disease registries. These can be subject to underreporting, and quality statistics are important here. They may have coverage gaps geographically or temporally, and usually researchers use passive rather than active follow-up, and this can be problematic if you have these geographic or temporal gaps. Regardless, medical follow-back is preferred if possible to improve the quality of the outcome assessment, and this has become more difficult with enhanced privacy rules pretty much all over the globe. So the last part of this section is to just talk about the exposure response induction period. This is because exposure today may be most relevant not for an outcome tomorrow, but for months or years from now. And this is particularly true for cancer and other chronic diseases, and for studies that have mortality as an endpoint. The most common methods of handling this are to use latency analysis. You could stratify a cohort and look at risk by time since exposure categories, but this can be difficult when exposures vary over time. You can also group exposure into time windows, and this is before a given time at risk. And there are actually pretty convenient ways to do this using incidence density sampling. I showed you an example of using exposure lagging, where you discount exposure just before the time at risk. You can also use what's sometimes called lugging, L-U-G-G-I-N-G, which is excluding exposure received at some distant time before time at risk. So then you have conceptually a moving exposure blackout window that is, or windows that are not considered relevant for risk. It's also important to note that cohorts typically try to capture some exposure variability measures. There are implications about latency from these exposure variability. Individual subjects can contribute person time to multiple exposure groups, which makes sense if you think about a cumulative exposure metric moving along over the cohort follow-up. This also adds to the rationale for using rates with person time in the denominator as the basic etiologic unit for a cohort study. And I'll close this part with just a brief presentation about the use of cohort data, occupational cohort data, for risk assessment. So we've mostly been focused on whether occupational diseases exposures can cause disease, but it's also important to know how much exposure causes how much disease. That is the exposure response relationship. And here's an example from a cohort study that I was involved in at NIOSH. These are uranium miners on the US Colorado Plateau. And these miners were followed for decades. And when we've published follow-up in 2005, we stratified information by smoking category and then looked at the lung cancer mortality rate ratio. So you can see that with radon exposure level increasing, the unit is called working level months, across each smoking category, there's an increase in lung cancer mortality. So that pattern is common. However, the slope differs from smoking group to smoking group. So this information is useful. It's called potential effect modification. Why are we interested in exposure response? One is for causal inference itself. observing a graded response in disease risk with increased exposure provides strong evidence for causality. These are suggestions from Sir Austin Bradford Hill that I'm sure many of you are familiar with. But it's also useful for risk assessment. Quantitative exposure response data is required for setting safe workplace and general population exposure levels. And there's an increasing tendency to try to seek information from occupational studies in studies in humans in general. So regulatory agencies will seek a safe exposure level that limits excess deaths or serious disease. So the idea is to count the number of additional deaths or diseases occurring with no exposure or low exposure at some unavoidable background level. However, the usual accepted protections are lower for workers than the general population. For example, for workers, we may be interested in a 1 in 1,000 or 1 per 10,000 excess absolute risk of disease. But for the general population, we would apply a more stringent criterion. And this is a societal decision. However, the levels of exposure that lead to those risks are where the science comes in. So for beryllium, this is an agent that has been studied for years. It's a lightweight metal and high-tech industry component that's been used since the 1940s to produce nuclear weapons, aircraft, and more recently, consumer products. It's produced in several US facilities, but used around the world. An occupational exposure limit in 1940-something of 2 micrograms per cubic meter, which is very, very low, was set to protect workers from a granulomatous, often fatal lung disease called chronic beryllium disease. However, it's long been known that this OEL is not protective. It's at least 10 times too high, and there was a suspicion of the cancer risk as well. So NIOSH conducted long-term follow-up of several cohorts of US beryllium processing workers. And more recently, we modeled lung cancer risk with intensity and cumulative exposure metrics. So a brief overview of this cohort. It was a pooled 3-plant cohort with about 5,500 workers and about 300 lung cancer cases. However, one plant had far more cases than the other 2 plants, even though it wasn't necessarily that much larger, or it was even smaller than the 3rd plant. However, it had much, much higher exposure levels for beryllium on an average basis. The cumulative exposure was lower or fairly similar to the other plants. This was a dynamic cohort and also an inception cohort. So it included workers hired before 1970 who worked at least 1 day, and they were followed through 2005. We used Cox proportional hazards regression modeling based on full risk sets, just like I showed you in that visual example. So the basic findings, if we stratify the cohort by the average exposure category, and DWA is a unit, like a time-weighted average. It's a daily weighted average exposure. And you can see that category means were increasing quite nicely across these categories. And we selected them not on the basis of quartiles, but more on the basis of, actually this particular cut was based on the best fitting cut point. So you see the baseline group is rather small here, with larger numbers in the higher exposure groups. You can see across these groups, there's quite good evidence of a very high increasing risk. And when we excluded those who may have been exposed to asbestos based on the job exposure matrix, as well as professional level workers, we saw similar results, if not even higher, in that reduced set of workers. So quite striking exposure response data. And just to illustrate the categorical results, this shows different models using different lowest cut points for that lowest category. So you can see when we used 0.2 as the lowest cut point, we saw a steeper exposure response trend than we used, say, 0.8 or 0.9 as the cut point. So yeah, the steepness of the exposure response was sensitive to that cut point. When we use quantitative modeling, we found that different exposure response curves fit the data better. So categorical and piecewise log linear model, both shown here, actually provided the best fit to the data, but you see there's this unusual plateauing of risk at the highest exposure level. That's a common pattern that we see in occupational cohort studies. When we tried to project the risk to the US population, we found that the average beryllium exposure that would be estimated to confer a 1 in 1,000 lifetime excess absolute risk of lung cancer varied by the type of model that we used. It was anywhere from 0.014 to 0.082 micrograms per cubic meter. So remember, the standard at that point was 2 micrograms per cubic meter. So clearly our study showed that the risks at the current exposure limit were far too high. So in 2017, OSHA issued a new protective standard for beryllium workers. They reduced that limit from 2 to 0.2 micrograms per cubic meter. And they did use the results of our exposure response analysis to inform about lung cancer risk at this new exposure limit, and recognized that the reduction was substantial in expected lung cancer cases, but still quite a bit greater than even a 1 in 1,000 excess lung cancer risk. So hopefully with this presentation, I have piqued your interest about occupational cohort studies. These are just some images of workers who have been subject to such studies, who've been part of these studies, and have provided incredibly useful information for helping all of us to understand what protective exposure limits may be needed. Key messages from this part of the lecture: occupational cohort studies have been and will remain, I'm convinced, important to understanding causes of disease. This is a complex design. I hope you've taken this away, that your simplistic understanding from Epi 101 of what a cohort study entails has been enhanced by this discussion. And these studies in exposed humans are incredibly important for risk assessment, not only for the workplace, but for environmental exposures as well. And with that, I'll stop. And just to mention, as I said, I have extra slides in case you are interested in attributable risk or in rates. All right, so I have